No, okay, I know what we can call this. We call this delta. Or, there we go, gradient x. Step 4, there is no step 4. No, there, yeah, I mean, pretty much. There we go, times the gradient of x. Yeah, G for gradient. Yeah, I used the upside down delta for gradient. But yeah, same thing. And this will do, yeah, step 5 is profit. This will do it for you. Like, this is the weight update for every single feature at the same time. You don't have to worry about, accidentally using new values to calculate your, or new values for earlier features later. It's all handled for you. It's like one dot product, a series of scalar operations on some matrices, and then there you are. Actually, let's see if I can... Come on. Sorry, I'm looking ahead in my notes because I do something similar here when we get to neural nets. Yeah, here we are. Why do we have xi in the matrix, but might write it as Napla x? I do not quite follow, but it's probably... Let me see here. Oh, this was mainly to match it up here. Nabla. Yeah, it was just to match it up there. So, like, since this is a single example, like, down here what we're doing, you technically don't need that superscript. Because, remember, I refers to the ith example in your data set. So, yeah, don't disregard that. Again, I'm really loose with my notation here, especially since we're kind of off in improv land as trying to go through what this example is. So yeah, don't worry about that. Could this be extended to the entire data set? Or would that not work with stochastic gradient descent because theta is updated for every data point? No, you can extend this to every data set. Let me think. So, okay. Sorry, Nabla, is Nabla the name of the upside down? Yeah. This is mainly to refer, like, I'm referring to this as the gradient of x. Because that's what this is. This is a matrix. This is the matrix of gradient values. And then you apply those gradients in step 4. So this is actually like a new, you can also think of it as like the gradient sub x as a subscript. You could think of it as G. This is just a way to refer to this matrix here because that's what we're going to use to update. Oh, yeah. Sorry, that's right. Gradient H. Theta x. There we go. We'll do that. Try to make things more clear. Boom. I guess technically it's gradient of the parameters, blah, blah, blah. Okay, so I'm going to warn you, this might be messy, me trying to do this extension here. But, you know what, let's see what happens. So, before I do this, is everyone okay with the single data point case? Does everyone see how this can greatly simplify things? Dot product, a bunch of scalar products, and then a scalar subtraction. And you've done it. You've updated your theta values. because, yep, I'm about to go off in the weeds here. The alpha is a number we select, right? Yes, alpha is it's a hyperparameter that you choose. It is the learning rate, and generally you want it to be small. Okay. Brent's potentially painful attempt to extend this to all data points. Okay, here we go. So first off, what's going to happen here is the dimensions of things are going to get slightly bigger. So x is now going to contain, so let's see, it is going to be, how do I want to represent this? We'll say it's an n by m matrix. So in this case, you've got, sorry, I'm going back and forth and back and forth. So x 0, 0, x 1, 0. So an entire data example is in one column. x2, 0, all the way down to xn, 0. Let me make sure, yeah, okay. And across, you've got x0, 1, x0, 2, all the way to x0, m. And then if we go down here, you end up with x, m, n. Would this lock you into a full batch? Yes, it would. It does lock you into a full batch. But if you want to do a mini batch, all you do is control the size of n. Oh, wait, no, not n. Sorry. I knew it was going to happen. M. So if, yeah, you can set that to be n or n plus 1. You're right, n plus 1. N plus 1 by m. Because we have x0. Good call. Good catch. Good catch. Okay. So yeah, if you wanted to do a mini batch, just change m. Like, don't use the full data set. Use whatever your mini batch size is. So we'll put a little note here. If m is not the size, or for mini batches, use m smaller than size of dataset. Cool. So that's x. Y is going to be a, say, an n, let me think here, m by 1 matrix. Y0, Y1, Y2. Now, one thing to keep in mind. M. You do not need to set these dimensions up this way. I'm doing this because I kind of default to columns. You could set your dimensions up so that all the multiplications work out nicely. But you do need to make sure that, you're calculating the thing you want to calculate. One of the hardest parts about using matrices, especially as you scale up in complexity, is keeping track of the dimensions. And when we get to neural nets, this is going to become especially important. So if you do want to set things up this way, make sure you keep track of dimensions. Because remember, you can only do dot products if your dimensions line up correctly. And it could be very easy to get lost in all of the transposes that you do in order to make things work. But anyway. So y is going to equal that, and our theta is still the same. It's still going to be a n. Well, n plus 1 by 1. Yeah. So theta 0, theta 1, all the way down to theta n. Okay, we've got this. Okay, the way I've set this up... Sorry, I've got to make sure that... Yeah, we don't want to do that. Oh, no, sorry, it's over here. So we actually don't want to do that. Oh, yeah, okay. Got lost. Okay, I knew it would happen. So step 1 is still the same. Calculate h theta of x. But now we're doing it for all x's. Yep, xt. I was looking at x and y, and it's like, wait a minute, that doesn't line up right. But yeah, no, it's theta, obviously. This is the exact same thing. X transpose, or sorry, theta transpose. Yep. Or you could do x transpose theta. Would theta transpose x also work? Yes. Yeah, theta transpose x would also work. But if you do it this way, the result is going to be a m by 1 matrix. And what this is going to be is it's going to be the hypothesis value for every single example. So h theta x 1. Not I, 1. H theta x 2. All the way down to h theta x m. There we go. So now we have them all. Cool. Step 2. Honestly, now it gets easy. Now it should be easy and kind of straightforward for me to follow. So yeah, we'll just call this our RH, our H sub theta array. Yeah, let's just call this H. So step 2, epsilon. So calculate raw error, which is epsilon. So this is just going to be a scalar subtraction still. So this is going to be h minus y. So it's still going to be an m by 1 matrix at the end of this. So this is going to be an m by 1 matrix that contains all of our raw error values. Thank you, epsilon. Step 3. Sorry, I've got a referring to this up here. Okay, yeah, that's the kicker. Okay. Sorry, I've got to think about this. Guess this is an m by 1 matrix. Okay, I thought it would be easy, but now I have to sit here and think. We're going to have m of these. Yes. So, let's see. We take epsilon, and... Right. That's right. Okay. So this is going to get multiplied by x. And we want to do it in a way that this expands. For this one, I had to use broadcasting. Yeah, again, I'm just keeping track of dimensions in my head. So this is an m by 1. X is originally an n plus 1 by m. So if you... Okay, so you could just do x dot epsilon and end up with m by n plus 1. Sorry. N plus 1 by m. M by 1. That's not right. Yeah, this is now where I get lost. So we got m by 1. Is there a way that I can do this easily? Yep. This is where I get stuck. So here's what I'm gonna do in order to not bog things down. I'm going to come back to this. Because again, this is not something I had prepared for today. Each element of epsilon scales its corresponding column of x, right? Hold on. Oh yeah, hold on. Maybe I'm overthinking it, which I tend to do. So yeah, we have our epsilons, and then we're just multiplying the original x, and then that's got to go into... I mean, yeah, each element of epsilon is going to scale its corresponding column, but then you also put that in every single example. Yeah, I'm going to, again, come back to this probably next time. That bothers me. So yeah, so as to not get bogged down, I will come back to this. So, installment 1 in Brent's potentially painful attempt to extend this was a failure. But next time, it won't be. So, that's fun. Oh, I'm gonna get you. I'm gonna get you. Okay. I'm not going to dwell on it. But at the very least, for, like, getting started, you can do this with the stochastic gradient descent method up here with the single data point. Look up NumPy array broadcasting. It's kind of hard to explain. Yeah, that's... I'm going to try to think of a way to explain things, but it will probably be on Monday. So that's something to look forward to. Brent redeeming his honor. But for the stochastic gradient descent case, for the single data point case, we've gone through a very easy way to handle things. And I can tell you that this will be good enough for this assignment. You can use stochastic gradient descent, and if you set your parameters correctly, things will work okay. However, I'm not going to let this sit. I don't like letting things sit. But again, in the interest of moving on, let us move on. Okay. So yeah, that's that. Yay. But now, we are still limited in a way. We have all of these features, but we're still only combining them in a linear fashion. And so, the question is, how to handle polynomials. or how do we extend this to polynomial regression? Question mark. Well, first off, why do we even want to handle polynomial, or why do we even want to model lines using polynomials? What's the benefit? First, what's the benefit? Sorry, I'm skipping forward. Yep. So the benefit here is that the higher the order of your polynomial, or the more, this reflects complexity, the complexity of your regression model. So like the higher order polynomials enable modeling more complex functions. And typically how we do this is through a process called basis expansion. And basis expansion is a fancy name for a very, very simple concept. Basis expansion. The idea behind basis expansion is what we're going to do is we're going to create a linear model, like a purely linear model, using higher order polynomials. So create dummy values, dummy features. Dummy features that are higher order versions of existing ones. So assume that you have, let's say we have an input vector of, I don't know, 2 values. Or 1 value, 1 feature. So this just contains x1. I guess we can go so far as to say it contains 2, x0 and x1. Sure, that's fine. So what you might do, or through basis expansion, what you would do is create extra variables that are transformations, or extra features that are transformations of these earlier ones. So let's create the set, we'll call it Z. Z is going to contain, maybe it contains 3 variables, or 3 features. Z0, Z1, and Z2. However, Z0 is just x0, Z1 is maybe x1, Z2 is x1 squared. Now, I arbitrarily decided this. And when you're doing basis expansion, you get to arbitrarily decide it too. So now, the linear regression, what this does is make the linear regression in Z space a polynomial regression in X space. So what we would do is we would do the linear regression in Z space, which means we would have 3 theta values. We would calculate like our hypothesis of Z would be equal to theta 0 times Z1 plus theta 1 times Z2 plus Sorry, no, that's wrong. That's wrong. Actually, no, we've got three things. So no, that's right. Z0 plus theta 1, Z1 plus theta 2, and Z2. So you'd want all the expanded ones to be nonlinear transformations. Exactly. Exactly. And you can go nuts with it. Like, you can do all kinds of fun stuff. So, for example, I could... let's see here. I could make another Z3, which is equal to x0 squared plus x1 squared. There's nothing to really stop you. But in general, what you want is, yeah, these extra features that you're adding to be nonlinear transformations of your original data. Does everyone follow? I'm hoping everyone follows. So in the programming assignment, when I say, hey, I want you to do, I think I go so far as to say, I want you to do polynomial regression with like a fifth order polynomial, and here's what the function should look like. And I think I give it to you not in this Z space, but I give it to you in the original space. So if you had just x equals x0, x1, and you wanted to do like a fifth order polynomial, you would create the vector z equals, let's see, z0, z1, z2, z3, z4, z5.